To drill offshore, you must isolate the rig from the ocean. That requires lifting a 50,000-ton steel structure completely out of the water and holding it in the air. The mechanical lifeline that makes this operation possible is the LeTourneau 375 Kip Elevating Unit, or EU. It is the sole system responsible for managing the vertical movement of a self-elevating jackup rig. Before examining the mechanics, a mandatory operational rule: you must consult your vessel-specific IOM manual before performing any work or maintenance on these systems. The elevating unit has a dual mandate. The first is active vertical elevation, powering the hull upward along the legs so the rig clears the sea surface to safely commence drilling operations. The second mandate is passive and static. Once the rig is elevated to its operating draft, the EU must hold the total dead weight of the hull plus all heavy topside drilling equipment securely in place. The system operates as a massive, precision-engineered jack. However, instead of applying force at a single, centralized point of lift, it relies on an extreme, highly distributed network of mechanical components to spread the immense load. This wireframe shows the Super 116E rig's 3 legs. Zooming in reveals 4 vertical cords per leg. Each cord connects to an elevating unit holding 5 stacked drivetrains, the 5-high inline arrangement. 3 legs times 4 cords times 5 drivetrains equals 60 motors and pinions. Lifting a structure that exceeds 50,000 tons defies standard mechanical lifting capacities. Spreading that unimaginable weight across 60 modular, synchronized nodes is the required first principle to raise the rig without exceeding the failure limits of steel. Distributing the load across 60 motors solves the weight problem, but we have to look at the specific point of mechanical contact where the actual lifting work is performed. This animation shows the core kinematic interaction. Each leg is fabricated with a continuous, heavy-duty toothed rack running its entire length. Meshing directly into that tooth rack is the climbing pinion. This is the final output gear of the drivetrain, driven by the electric motor. When the motor turns, the pinion rotates against the rack. Because the leg is resting firmly on the seabed, the rack is fixed in place. The pinion cannot travel down, so its rotation forces the only movable element, the hull, upward. The physical principle is a simple kinematic inversion, but to execute it against tens of thousands of tons of static resistance, the system requires an enormous multiplication of torque before the energy ever reaches the pinion. That brings us to the central mechanical question of the EU. How does a standard commercial electric motor generate enough raw torque to turn a pinion under thousands of tons of compressive load? This cross-sectional schematic traces the kinetic energy from its electrical source, flowing left to right through the drivetrain. Power enters at the number 5 motor. This is a 600-volt, 3-phase AC induction motor. The motor drives directly into the first reduction stage, the number 4 gearbox. This is a fully enclosed, oil-lubricated unit housing a 2-reduction helical gear set. Inside this single gearbox, the rotational speed is aggressively reduced, and the torque is multiplied at a strict ratio of 69.33 to 1. Power flows out of the gearbox and into the second stage, the 1-pitch gear set. This section remains enclosed and fully oil-lubricated. Next, the power transfers to the third stage, the half-pitch gear set. At this point, the mechanical transfer shifts to open gears, which require heavy grease lubrication. Finally, the kinetic trace terminates at the output, the quarter-pitch climbing pinion, transferring the vastly multiplied force directly into the leg rack. By running the rotational energy through these 3 distinct gear reductions in series, the system achieves a massive compound mathematical result, a total gear ratio of 2082.67 to 1. In physical terms, the number 5 motor must complete over 2,000 full revolutions just to turn the climbing pinion exactly 1 time. This highly specific staging of torque multiplication is what drains the speed from the AC motor and transforms high-velocity electrical rotation into immovable mechanical leverage. Operating 60 drivetrains simultaneously on rigid steel racks introduces a critical engineering danger. If the motors output varying levels of torque, the load distribution becomes unequal, causing the faster motors to absorb the rig's weight until their gear teeth shear off. The system passively solves this synchronization problem through the design of the number 5 motor itself. It is a high-slip AC squirrel cage induction motor. The high-slip architecture means the motor naturally sheds speed as mechanical resistance increases. If one motor starts pulling ahead, it encounters more resistance, slows down automatically, and allows the other 59 motors to catch up. No single motor can hog the torque, but load sharing only matters when the power is on. The ultimate blackout scenario is a total loss of main rig power while elevated. We need to look at what prevents the 50,000-ton hull from simply free-falling down the racks. This schematic details the integral fail-safe brake, which is directly mounted onto the shaft of every single number 5 motor. The mechanics of the brake dictate that it is spring-applied by default. Heavy internal coil springs physically drive the brake pads into the friction disc, locking the motor shaft in place. The brake is only released when incoming electrical power energizes the internal electromagnetic coil, pulling the pressure plate back against the springs to free the shaft. This establishes the ironclad rule of the jacking system. No power means the brake is on. If the rig loses electricity, there is no delay and no manual intervention required. The loss of voltage automatically and instantly drops the electromagnetic field, allowing the springs to lock all 60 drivetrains. The rig physically cannot drop. Moving from automated safety to active control, the operator commands the jacking system through a dedicated control panel. This interface handles 4 distinct operational modes. The first is raise hull. In this sequence, the PLC logic powers up all 60 motors simultaneously. The electromagnetic brakes release in unison, and the pinions drive the hull upward. The second is individual leg control. Instead of synchronous movement, this mode isolates power to a single leg, allowing the operator to make precision leveling adjustments. The third mode is lower hull, which introduces counterintuitive physics. When descending, gravity is doing the work. The immense weight of the hull actively pulls downward, physically driving the pinions and forcing the motors to spin. Because gravity is turning the rotors, this diagram illustrates a sudden phase shift. The AC motors stop consuming electricity and transform into electrical generators, pumping voltage backward into the rig's grid. This is known as regenerative power. To prevent this massive electrical backflow from burning out the system, it must be safely routed to and absorbed by the rig's resistor bank, where it is burned off as heat. The final mode is emergency jacking. Operated via direct push buttons at the switchboard, this mode physically bypasses all PLC logic to force motor operation during severe control failures. The LeTourneau 375 manages forces that would destroy standard industrial equipment. It survives not through brute strength, but through 60-part modular replication, a precise 2,000-to-1 mechanical advantage, and inescapable fail-safe logic. In Episode 2, we will open up the casings and deconstruct the internal components of the number 5 motor and the number 4 gearbox in granular detail.